Hey guys, welcome to Sopi Mix Studio Umbiamas, conectando Aruba com o mundo via vídeo podcasting. Conectar conosco, compartilhar ideias e histórias para nos inspirar e para nos abrir. Sopi Mix Studio é plataforma de podcast na Aruba. Follow-nos no Facebook, subscribe no YouTube ou na plataforma de podcast preferida. Escute o podcast preferido que hora e onde está. Sopi Mix Studio, powered by Qredits, botiu ideia? Qredits educa e prepara abo para vir um empresário exitoso. De business plan, guia personal e préstamo para negócio até com 100 mil florim. Vira para mês donho com Qredits. Sopway. Passa na Sopway para o sop, salada, wrap ou flatbread e mais fresco. Com 7 localidades rond Aruba. Nós está cerca de Ibo. Sopway. Swingmasterz. Organizando events, conferences of weddings, mister de luz, sound, staging, DJ, trussing of flat screen, Swingmasterz está claro para ser boa fiesta éxito. Swingmasterz. E agora, Sopi Mix Studio é plataforma de podcast de Aruba, está apresentar.
We are live. Good afternoon, everybody. And good morning if you just woke up. Today, Bruce Harms and my father are not going to be present, and so we have a familiar face that you might recognize on this show and some others. Elton Lampe. Please,
Hi.
introductions.
Hi Jean-Luc, how are you doing? Good? Yes, thank you for the invitation. We're gonna be for a ride today for a very interesting topic, so let's rumble.
So before going onto the show, let us go over our sponsors, Subway, Qredits, and Swingmasterz for allowing us to have this amazing studio and this entire setup. So, a very, very brain-wrecking topic we have today.
Yes.
Dark matter and dark energy. And I would like to preface that I personally am not an expert, full disclosure, just somebody with an interest in astronomy and the likes.
Yes, me too. My background is engineering. I always had a interest in astronomy, and I follow the development of astronomy since the history of time, looking at the books and then seeing how we are going. So a few weeks ago, to mention, we were discussing this topic and say, oh, this could be a nice topic to discuss here.
Yeah.
About this.
Nice. Well, the universe loves irony, now doesn't it? So, dark energy and dark matter. I'm very certain that a lot of people who would watch this show would or listen would be aware of the terminology, right? And would have a rough idea of what it is. They most likely have heard of it but never delved deep into it. How would we explain the concept in layman's terms?
Well, I think first we need to start with the forces. No? What are the forces that we have, that known forces? So we start very small. We have like charging. Charging force is like static energy.
Oh,
It's when you, I mean in Aruba you don't feel it that much, but if you're in Arizona when it's dry, you can feel it that when you're going to touch like a car and you feel like a discharge, you feel like a spark going from your finger to the car. So that's the energy, they call it the electric field, charge energy. And that's also an energy force that you cannot see.
Yeah.
You cannot see, or you can see it, but when you're very close, when your finger is very close to the car, you see the spark. Sometimes you feel it, but you can see the spark going from your finger to the car. So that's one of the smallest form of energy. when you go to another force that's magnetic, magnetic, we all know that you can see that a magnet attracts ferrometals.
Yes,
So,
yes.
and that's also an invisible force.
Oh,
So
definitely.
You can, when you pull the magnetic close to, you can feel it that it attracts.
Yeah, you can only feel it, but there is very, very little to have visual aid to the force, right?
And those energy forms were known because you can see it actually working. Magnetic has been around since forever.
Yeah. I think
the more recent reason is in the past 100 years is gravity.
Gravity, yes.
Gravity itself is very new. Because you cannot. The gravity force is so weak in terms of where we're living and on Earth. So you will need a lot of mass to have gravity to pull something. So But it's a weak force to measure it on a scale of human scale. Let's put it this way. But it's a very strong force if you look at it as like Earth. It's a mass, and because of gravity, it can hold the moon in orbit. The sun also is a mass, and it can hold the planets in orbit.
The entire solar system.
Correct.
Yeah.
So that's the gravity gravity force that we're talking about matter. But when we're going into dark matter, it's another kind of force that holds galaxies and the whole universe. It acts differently than gravity. Because it acts differently, they call it dark matter, because you cannot measure it in terms of matter. Because matter, you can see it, galaxies, planets, anything. But this is not matter, but it still has a force. So something is behind it.
Exactly.
And so by going from small to big, that's how we can start feeling what dark matter is.
Here we have so the explanation. This is related more to dark energy, if I remember correctly, right?
That's more related to dark energy.
Yes. So here we can see the birth and creation of the universe, right?
Yes, correct.
And we know that the universe is expanding as we speak, right? But
but we know that it was actually a surprise that it's expanding. Because if we applied the gravity forces, basically gravity is like a how we call it, a spring. So that's why comets returns. It goes away, then it slows down, and it comes back to the matter, to the mass. But so that's why they was pre-assuming that the galaxy
would collapse.
Because the Big Bang was a big explosion shooting everything far. And then everything will start slowing down and coming back.
It would the great attraction. The universe would eventually slow down because gravity.
Yes.
And it would
slow everything down and then pull it back to one point.
But
then the Big Crunch was the idea, the Big Bang and the Big Crunch.
Yet it accelerates.
But that accelerates, that throws all of the scientists.
Not only is it growing in size, so already gravity is out of the question. It is accelerating, so it is a greater force.
Because growing, it could be growing, but slowing. Slowly slow down till it reach like a
maximum.
That it starts maybe crunching or stay at that point. But because it's accelerating, there must be a force that's pushing it. And pushing force is not gravity, because the gravity is known as pulling. So that's the thing right now. We know that like you said, you know that the universe is expanding, but there must be a force doing it, and that force they call it the dark energy.
Yeah, because that's the force that is moving.
That's the force, energy, dark energy. Because dark matter is something a little bit different, but we're gonna talk about that too.
All right. So a small recap for those who just woke up or aren't really listening, or this is all new terms to them, right? So we have the multiple types of forces, right? Yes. We have charge force. So imagine that small little shock if you lived in Holland after you rubbed your clothes a little bit too much, right?
Because it's not metal.
Yeah.
And that's also the force that when you're going into like a substation with electrical energy, and if you're getting too close to the conductor, it will pull your charge to the conductor. So that's why it's so
dangerous.
Yes, correct.
Is it also?
It's not metal. It's not magnetic.
Yeah,
but it's another type of force.
And then we have magnetic. Quick sidetrack. Yeah. There is dark matter, normal matter, and then dark energy that would make up the entire universe. And keep in mind, like when you gaze into the night sky, you only see specks and a lot of black space, right? Or quote unquote empty space. And
that's why it's called space too. It's space.
Yeah.
It's related to that. Yes.
And by our current understanding, because this is still a very, very ongoing study, right? And research, dark matter and dark energy consists the most out of everything, right? Yeah. The crazy idea is that maybe in 10 years, 20 years, 50 years, as we get more technology that could possibly calculate everything and detect different ways, right? We might be wrong. So this is still a very, very ongoing thing.
What's known is what has been measured.
Yeah, so far.
We measure that it's something is acting, but exactly knowing what it is, there's a lot of things that we might discuss, some crazy ones, but that's the idea.
But to continue the small recap, right? We have a charge, which would lightning be a good example of that?
Yes. Because the clouds get rubbed.
Yeah, and then it strikes.
And then it strikes.
Yeah.
That's a force.
Then you have magnetics. I'm very certain that many people are familiar with magnets, right? And then you have gravity, the weakest. The reason why it is viewed the weakest is it takes the entire Earth, the mass of everything that we are standing on, to keep us to the ground, but it only takes small little magnets to lift something in the opposite direction.
Yeah, if you take two masses and put it together, you won't feel any force because the mass is so small. But once it began to become larger or denser or both, because denser means that that's why the volume of a feather, not mass, but volume, and the volume of lead it's denser. But if you're talking about mass, you have different sizes.
Yeah.
So that's why a kilogram of feather is so big, and a kilogram of lead is like a big small chunk. But that's because one is denser. But the idea is, if the mass is denser, it will have more
gravity.
More gravity.
Yeah.
Yes.
And then we go into we have charge, magnetic, and gravity now. And then would dark energy be considered a force then?
Dark energy is kind of a force, but dark matter first. What is dark matter, and why it's still called like a matter? It's called a matter because it's closely related to gravity, but the rules are different. So what they looked at the galaxy. So that's a collection of all stars together in the galaxy, and they saw that by applying the rules of gravity, the stars moving in the outskirt of the galaxy shall be moving slower than the stars closer. It's like our star.
Yeah.
So if you look at the orbital of maybe Mercury,
yes, the
going
first star.
faster around the sun than Venus, and then Earth,
and then Pluto.
And Pluto take years. So take years to go into orbit around the sun. But Pluto is not a planet.
Oh yeah.
Okay. Not
planetary celestial body, celestial body.
Satellites.
Yeah.
Okay. No, but it's only a joke there. But in the galaxy, so they were assumed that the stars will move with a slower, when the outskirts will move with a slower speed than the ones more in the center, applying gravity rules. But when they looked at the galaxy, they saw that the stars in the outskirts move with the same speed, or even faster than the ones closer to the center.
At the rim.
At the rim, yes. So there must be another type of matter or another type of force or a kind of gravity, dark gravity, and that's pushing or that's trying to make the stars move faster.
Yeah.
Because the idea of gravity is that the star wants to go straight
into the direction.
The first law of Newton, yes. But because the gravity lets the star keep falling, or planets keep falling. At a certain time, it will balance out, and it will stay in orbit.
Yeah.
If the force is stronger, it will come and crash to the center. If the force is weaker, it will go away. So planets and all the planets orbiting our star, the sun, is moving in a balanced force with the sun, and our moon too. But even though it looks balanced, they say that the force is just a little bit weak. That the moon will go away. With time.
Pull the picture back up. So, as far as we understand, there is a supermassive black hole, right, at the center of our galaxies, right? A huge, unfathomable source of gravity, right?
A mass.
Mass, basically, for all intensive purposes, an infinitely dense center, right?
Correct.
Yeah. And so we now know quite confidently that stars near the center of the galaxy spin very, very fast around it, right? And but that's within there. But also other research has shown that the very tip of the galaxies, the stars, should, with the speed that they have, actually just fly away as well, right? But they just stay. And so they're with both of these reasonings, the only conclusion is there's got to be something that's keeping the galaxies together, right? And then that's where the idea and the conclusion of dark matter came in, right? And the core difference would be that since it's more of a matter, it is much more tangible and like glue-like then, right?
It's more like it's a force that pulls. Dark energy is a force that push. So expanding of the universe is about dark energy. Yeah. And holding the galaxy together is the force of dark matter. And what I just explained, that some gravitational formulas does not apply at certain galaxies, and there must be something else that letting the stars moving the way they do with constant speed or even faster than one in the closer to the center.
So to put it simply, without taking dark matter into consideration and our current understanding of gravities and like acceleration, stellar bodies and everything, right? Galaxies shouldn't work, right?
Yes.
And so that is what dark matter fills in. It is that missing glue that then explains why these huge bodies of stars and everything can stay together while moving at very, very, very high speeds. Yes. And so dark matter pulls, right? It keeps it together. So
it
then
pulls, but in another way than
gravity. Yes. It's believed it's theorized. It is like dreamt that if we learn how to make and harness dark matter, we might be able to make anti-gravity stuff, right? Or is that pure sci-fi nonsense?
Well, it's nonsense until proven. In a sense, until proven.
Yes.
But it's everything is nonsense 100 years ago about anything. So there's a lot of theory. There's a lot of theory about, but I think about anti-gravity is more using antimatter. Don't confuse dark matter with antimatter. Antimatter is the opposite of matter.
Yes.
Antimatter is a matter
of the opposite charge.
It's an opposite. It's hardly to grasp. But it's an opposite matter that once it collides with matter, it will disappear. So it's matter, but that will disappear if you
touch it with matter.
So that's antimatter. That's another. That's why they say if you have antimatter, you can create anti-gravity.
Oh.
Because that's in the same realm. So antimatter, they created and
they are currently making.
Yes.
Yeah.
Because it's so unstable, and to make it's the most expensive.
It is most expensive material
stuff
known to man right now. Yeah.
Or we should say it anti-stuff.
Anti-stuff.
But it's the most expensive stuff because to make antimatter, it's
Hadron collider. You need that entire thing.
Yeah.
And a
large hadron collider.
Yeah.
And crashing, and then you can create antimatter, and with the idea is when you start controlling antimatter, you can do anti-gravity. And you can, also when you collide it with matter, it will disappear, but it releases a lot of energy.
Yeah.
You can use that energy for anything. You can solve the energy crisis and everything. So
maybe.
That's why antimatter is so
heavily researched.
Yes.
Yeah.
Yes.
But so then dark matter is the glue.
Yeah, dark matter is a matter that you don't. It's not antimatter. It's not matter. It's just a matter that
we don't see.
That you don't see, and don't see is not only in our spectrum that we can see, but you cannot see it, measure it in any kind of spectrum. So not even in infrared or in ultraviolet. So it's a radio frequency. You cannot see it and measure it by any kind of measurement that we have right now. But by looking at the behavior of the stars, of galaxies, you know there is a force out there that's glue it.
Yeah.
And that's why it's something that you can not see. That's why dark. Let's call it dark.
Invisible matter.
Invisible matter. Yes. Invisible matter would be more dark. Dark goes like a
magic. Dark, dark force.
Dark force. Yes, correct.
But then let's move on into the even harder to grasp one: dark energy.
Yes.
Right. The currently theorized cause as to why the universe is accelerating away from the center, right? So, is that all we know essentially?
In measurement, yes.
Yes.
In theoretical, there's been a lot of ideas. I could say it's all nonsense until it's proven. One of the theory is like. It's a multiverse. Once you say the multiverse, you start thinking about Marvel or about magic, about anything. Multiverse is having the same universe but with different kind of timelines or different physical properties.
There are multiple interpretations of the multiverse, right?
Yeah.
So you can
that's
have
what makes it so difficult to grasp.
Yes. You can have like parallel universes, multiverse, where like there's different timelines and everything. But there's also the interpretation of the universe is a small little shell in the omniverse, and then there's sibling universes floating around it as well. But that we have.
No, that's what I mean. Multiverse itself is a topic that has so many branches, depending on what you're. Let me see. This is the glue of the total universe as we know it, measured in microwave.
So this is the background. What was
everything
called?
that's out there and that we can measure.
Yeah.
So
this is the observable universe as far as we know.
And what we're looking here at is. What we can see there, like the blue spots, maybe the dark areas, and the red spots, those are superclusters. So, what are superclusters? Okay, the galaxy, the whole galaxy is very, very, very big.
So, yes. We are in a surprisingly big galaxy.
So if we can start again from small, we live on the Earth. Earth is orbiting the star. One star is our sun. And our star is orbiting our galaxy. We call that the Milky Way.
Yeah.
And the Milky Way is part of different galaxy that forms like a local cluster. We call it the Virgo cluster.
Yeah.
And the Virgo cluster itself is part of a bigger cluster called the Super Virgo cluster. And then when you go to all these super clusters, you get to one big supercluster, and the local supercluster that we call the local. That's one of the red things that you can see. The local supercluster is called the Laniakea.
So pull up the picture back, please, producer.
Yes.
So is one of the yellow-orange specks?
That would be a supercluster that we have.
A local supercluster?
Local supercluster.
Millions of galaxies.
Millions of galaxies in that, yes.
Yeah, I can't really.
It's too big to comprehend.
We are literally. That is then a pixel here, essentially.
Yeah, that's what it's
insane.
A pixel here. And insane because there's so many galaxies in it. It's insane, and space itself we cannot even comprehend to talk about.
There you go. Yeah.
Yes. That's the idea. That's the clusters.
This is our
the Virgo cluster, like there. We are in the Virgo cluster, more in the.
Oh, over there! Yes. It's pretty big compared to the other ones. Yeah.
And that's part of the local galactic group that we call Laniakea.
So this is the entire
local group. That's one of the red dots in the entire universe.
Insane. And then here itself, the space between the white dots is millions of light years.
Oh yes.
Yeah, the distance between those little,
is millions of light years. Yes.
Insane.
And those dots are galaxies, and are thousands of galaxies. So our cluster is our close cluster with Andromeda.
Yeah.
And with 300 stars, that's called the Virgo cluster. That's part of the Virgo supercluster, and that's part of the Laniakea. That's a local galactic cluster. And the local galactic cluster, there's a lot of galactic clusters that forms the universe. And like you mentioned, distance is out of the mind.
Unfathomable.
Yeah.
Literally.
Let's just talk about light year.
Light years, yes.
Light year. What is a light year? Can you comprehend how long is one light year? I mean, that's the year that the light travels from point A to point B. If you just take 1 second, light can travel around the world 7.5 times in 1 second. So if you can say 1, 2, 3, 4, 5, 7 in 1 second, each 1, 2, 3, 4, 5, 7 is entire loop of the light. So imagine around the world in 1 second, 7.5 times. That's a light second.
Wow.
Imagine how far it would be for a light year. Yeah. So that's just even for us, a light second is large.
Yes. And this is Milky Way, right? Or is this Andromeda?
Well, we cannot pick. This is, I think it's Andromeda. Sometimes they put pictures of Andromeda and say that's Milky Way.
The Milky Way.
Nobody's gonna take a picture of our galaxy.
Yeah.
But that's difficult. But yeah, that's the Milky Way has the same structure as Andromeda. And Andromeda is the closest galaxy, and it's the only galaxy that we can see with our naked eye.
Oh, on a good night.
Yeah, on a good night. Very good night. A very good night. Without clouds, without anything.
No light pollution.
Yeah. And you can see it as a very faint star, but it's actually a galaxy.
Wow.
And we know now that's more galaxy than stars in our Milky Way. So it's astronomy is very. Once you start talking about it, we feel so small.
Yeah. Existential crisis.
Yes.
But back to dark energy, and so essentially talking about this puts every. Yeah, go ahead.
Before we go to dark energy, what I mean with
multiverse?
With the multiverse is Neil deGrasse Tyson was also theoretical about this. Because once you see that scientists are talking about multiverse, because it's something that might be possible, it's something serious.
Yeah,
it's not that we are looking at superhero stuff.
No, of course not. Yeah.
It's something serious. So, and he mentioned that multiverses could be in the same kind of place, but because they're different universes, different multiverses, you cannot. The only interaction could be this dark matter.
Dark matter or dark energy?
Dark matter.
Oh.
Because the matter of the one universe affects the other. You cannot see it, but it affects it. So that means that the galaxies could be in the other universe closer or stronger, and then you can have it affect our galaxy.
Wow.
If you talk about multi-layer, multi-dimension, the same. So you cannot see it, you cannot measure it, you just know it's there, but it's the influential of the multiverses. Yes. Yeah. That's the idea. Exactly. So if you look at one of the dark spheres, so let's say the blue one is our universe. Yeah. And the multiverses is lots of different.
Yeah.
And the multiverses around our universe are influencing our universe in a way that we cannot measure it yet.
Of course.
But we know it's there because we can measure it, but we cannot see it, or we cannot understand what it is.
There is an unseen force.
Unseen and ununderstandable force, but it's measurable. It's affecting our universe.
Yeah.
We cannot understand yet what it is. And one of idea is this multiverse theory, right? And that's also bringing string theory. That's another big topic. What it is. Quantum energy, looking at the micro instead of the cosmos.
Yes. Brain breaking, brain racking. Yeah. I hope you're having a great Saturday, dear listeners.
We need some Red Bull or energy drink. Let's put that. Not the marketing.
Yes. Then, but that's still on the dark matter side, and then
the dark energy is just is the expansion. And when you talk about dark energy, is energy that accelerating things, forces, forces that's pushing everything, and matter is forces that attract. Dark energy is forces that
repel.
Yes. And not. But because even if a Big Bang shoots something away, you would assume that it would propel it with a constant speed, like the first law of Newton, that everything goes in a constant speed. But if something is accelerating, it must have a force pushing it.
Yeah, it must have energy to continue pushing it faster.
That's it. And because the universe is expanding and accelerating matter. And accelerating forces, there must be an energy that's doing it. And what is it? We don't know. We just know that it is there. The universe expanding, accelerating, and we call it dark energy.
So the only thing that is currently is very we're reaching the limits of explanation and vocabulary right now. That goes faster than light is the expansion of the universe itself, right?
Yes.
The mere fabric is growing larger than sometimes light can go across it, right?
Yeah.
So
some galaxies that emitting through us will not reach us because they're expanding faster than what their lights are shooting back to us.
That's an insane thought. So the universe can be so much bigger than the observable universe simply because of that fact.
Yes, correct. Because we cannot see farther than the speed of light.
Yeah. The speed of light is the heart, our little vision bubble. Yeah. Crazy.
It's the same as a black hole because it's so dense. Lights cannot escape from it. If the light starts shooting to us, because it pulls it back, the light will not escape a black hole.
Wow.
It doesn't mean that the black hole is a hole. Actually, it's mass. But it's so dense that the lights cannot escape it. That's why it looks dark. That's why it looks black, and that's why it's called like a black hole because everything will keep on its surface, will not escape.
I've heard that instead of it being a literal black dot, it would be more like a blurry spot in space, because as light goes into it, it will circle it. Yeah, event horizon. It will circle it a few times.
Yes.
And that we are lucky to escape. But once it enters, it's gone, right? Yeah. Or gone for us to be able to.
And laws of physics goes crazy when you're reaching when you
get past the event horizon.
It slows down time. When you see something at the event horizon, you look at the past because it slows down, and then it will look like it's not moving anymore. But that's everything with space-time and dense matter.
But so what if we somehow figure out... Sorry, listeners. I hit my microphone. What... Dark energy is the only thing that's currently, or as far as we understand, propelling the universe or the material fabric of the universe itself.
Yes.
Right? If we can somehow capture that or somehow figure out how that works, right, then we could solve the faster than light problem that we have with spacefaring, right?
It's good. Yes.
Because we need to be very, very creative with circumventing the hard speed limit of the universe, which is light speed, right?
But the energy, the energy accelerating the expansion could be because we can have multiverses that's at the same place at our universe. But we can have multiverses that, as we look at the picture, that have like universes far away. That's another universe that's pulling our universe apart.
Oh,
you know, that's and because it's pulling it apart, it's accelerating it to a big. Yes, the one that we have with all the balls, the dark and the blue one. So that's what I mean with multiverses can affect our universe because they're pulling from all sides energy from the outskirts of our universe. But if the multiverse itself is in between our universe, so maybe we're sitting right here on this location, but there's also another Jean-Luc, another Elton in another multiverse in this location, but we cannot interact it because their atoms or something are different, that we cannot see it, smell it, and anything. But they interact with the space that we're here. You know, so that's what they're this philosophical theory or hypothesizing about multiverses affecting our universe, and that's why you have dark matter and dark energy. Yeah, it's insane. It's, what is insane, and what is maybe our grandchildren talk about. No, this is so simple.
We have a simple mathematical equation to
parallel worlds are just like common as as discovery of the Americas or something. It's a topic that's. It might look science fiction, but it's taken very seriously in the scientific world. Astrophysics about parallel universe, multiverses, dark energy, dark matter. So there's a lot of unanswered questions now. Yes,
huge. So
the more we explore, the more we find out what we don't know.
one unopened box, once we open it, leads to more unopened boxes.
But that's why we're here to, At least we're sharing what we know, so our listeners can see or can hear what's out there.
I was researching it, of course, this morning, right? Hoping that in the last 5 years that I haven't looked into this out of interest, that a recent discovery has been made. But as far as I'm aware, there hasn't been a major development, right? No. Are you aware of any?
No, that's the idea why they made the James Webb telescope, because the Hubble can see so far, but the James Webb are more equipped with infrared, with other frequency to look deeper, to start to unlock the secrets. We know it's there, but we want to unlock a why. And we know it's there, but we want to know how it's working and why it's there. So that's why the James Webb telescope is so important right now, to look farther, or to look in more detail at the farthest at the galaxy that's more far away. You can see basically at the origin of our the Big Bang, because what you see right now is not what is happening right now.
Yeah,
because the light travels.
It's old.
it's old.
It's old.
The more farther the object is, the older it is, because the lights that what happened is now reaching us, but it happened so many years ago. So
a good way to explain that is if we put which is the nearest star that we currently have.
But even if we look at the sun,
it's 8 minutes.
It's 8 minutes from the sun.
Yeah,
8 minutes. So what we see at the sun right now was 8 minutes ago.
Yeah.
Because even though the sun is close in astronomy terms, it's far because 8 minutes. Yeah.
In light speed.
In light speed. In light speed. So the light that the sun emits, it takes 8 minutes before reaching us.
So if it were to explode right now, we will find out
it
8 minutes later. Yeah. Insane.
It's insane. But imagine that's the sun, and we see the sun is so close. We see that big, that's we
ball,
can feel the energy and everything. But imagine a star that's
millions of light years away. So
even the closest star, Proxima Centauri, I think.
Oh, Centauri. Yeah.
The Alpha Centauri was thought to be the closest, but in time they saw like a dual star moving close to it, and that star Proxima Centauri is the closest. But both are very, very close. But both are around 4 light years.
4 light years.
4 light years. So if that star explodes right now,
it will take 4
years for us to notice. That's the closest star.
Wow.
So imagine if you go to farther away, and then you will reach at the outer scheme of our universe, that you can see a galaxy like around 13 billion light years that it took. So that was one of the first galaxies, because they calculated that the Big Bang was 13.6 something billion. So that was one of the galaxies that was there in that time. The first galaxies was formed. So now it's so far that now the light of that galaxy is reaching us.
Oh my!
So we can see back in time what happened.
Wow.
13 billion years ago. It's yeah.
But yeah.
And what is a billion? A billion,
what is a billion? It's a million millions. Yeah.
Yes.
Webb's orbit. So here we have a small.
Yes. The orbit of the
this is how we're going to be able to see better into the distance, right?
Correct, because the farther you are from Earth, the more span you have. Because once it orbit, you will have a far reach from the left side. Let's put it that way, and one reach at the right side, and then you can have like small angles to determine distance. Because at one angle you will see the stars so close, and the other angle so close, and then you can use simple angle. Yeah, I mean, no, but very simple. What do you call it? With angles?
Geometry.
Geometry.
Yeah.
You can add simple geometry formulas to calculate distance of the stars. But if you measure from the Earth, I mean, the angle will become so close that you cannot see the difference. So that's why measuring from farther away would benefit. And having that practically in a kind of a day. Because we can measure from angle. That's why what we did with the Earth orbiting the Sun.
Yeah.
In summer, we can measure all the stars. And then when it's other side of the Sun, we'll measure again. And we will see angles and these things. But we have to wait each
half a year.
Correct. We need to wait half a year to make those measurements.
Damn.
But having the James Webb in an orbit, in a large orbit, we can measure that very
relatively
in a day
quickly.
or two, or Yes.
So yeah, that's a model, a 3D rendering of the Webb telescope. But I feel like that would be its own episode to talk about the technologies that we have.
It's farther more. It has farther more capabilities than the Hubble.
Yeah. So
Hubble was practically a lens that look at the lights at a certain frequency of the light. But James Webb has so many more features. So we can look at the James Webb one and talk about what. I mean, once that the images starts getting and they find some discovery, it's a great time to talk about it.
Oh yeah, definitely. So I do not feel like we can expand further.
Yeah.
Get it? On these topics. A brief recap.
Yes.
We have all of these different energies we currently forces. Thank you. That we understand. Static. So imagine lightning and that small shock that you get sometimes when the air is dry. Magnetic.
Yes.
No further explanations with that. Gravity, which is very, very weak and consistent yet with huge masses. Then we have dark matter, right? Which is
invisible matter, invisible things that pulls things.
Like gravity, but different.
Without a mass.
Yeah. With no mass as far as we know and understand, right?
Yes.
And then we have dark energy, which is currently the reason, as far as we know currently, of why the universe is accelerating away, right? And if you want to understand where these things come from, how they work, and why they work, have fun philosophizing and theorizing about multiple reasons, such as multiversal ideas.
That's correct. Yes. That's how we are right now.
Insane.
Maybe in a week or so, there's a discovery
or something. Imagine later today a new discovery is made, right? Or announced.
In our universe, not in the multiverse.
Yeah.
Okay, yes.
Thank you so much, Alton, for
the invitation,
for coming.
I know it's a topic that's once you talk about astronomy, we feel so small. Because it's incomprehensibly large.
Yes,
that's what we're talking. So that's why so many space and dark energy and dark matter is part of that huge cosmos. And now that's what we can share, I think, today about at least to start grasping the idea.
Definitely. I hope that the dear listeners and viewers have been able to roughly keep up with this topic. I definitely have studied for like a week in this one morning and 1 hour.
No, it's a kickoff topic. So to start thinking about what's out there instead of every day talking about what's here.
Yes.
So there's a whole study outside of this world, astronomy.
There's a whole universe.
There's a whole universe
out
to talk
there,
about.
Yes.
And we didn't even talk about is there life out there or
on top of it,
civilization.
Yeah, Fermi's paradox.
Those are topics on itself.
Quick thank you to our sponsors, Subway, Qredits, and Swingmasterz, for having this show be hosted and exist.
Yes.
And any final words?
No, I want to thank Sopi Mix. I want to thank you, Jean-Luc and Bruce, for for the invitation and for the great work, great topics, different topic that you're bringing every week. So
thank
nice.
you.
Keep up doing it. And anytime, any topic, I would do my part if you invite me and do.
Of course.
It's nice. Thank you very much. Thank you, listeners, also for
watching and listening. Yes. And see you next week.
All right. Thanks.